Hello and welcome to Diksha Karnataka YouTube channel. So in the topic under 30-minute session today, I am going to discuss a very short topic which is series and parallel combination of cells. Many students do confuse and make mistakes over here. So this will be a KCET focused session for all of you. If you really want to score well, this topic is super duper important. Every year 1 to 2 questions directly comes from this formula based, basic concept based, so you need to understand. And obviously in many cases in PU boards also the derivations etc are important. So without any delay, I will not take too much of your time. Let's start. But before I start, just a request that if you are watching this for first time, don't forget to subscribe to our channel, or if you are watching it again and again but you have not subscribed to our channel, don't forget to subscribe to our channel, because that's what inspires us and that's what gives us the mileage to go forward, right? Let's start. So EMF, internal resistance and terminal voltage, these are the three terms that we hear very often. So let us understand what is EMF. EMF stands for electromotive force, right? Work done per unit charge by the cell to drive charge around the full circuit. It is the open circuit voltage of the cell. Okay, so open circuit voltage means if you have the cell but it is not connected in a circuit, just open, and if you have a device to measure that potential, that is called EMF of the cell. Basically it's the maximum voltage that the cell can give. Okay, but obviously the maximum, whenever we say, we are not getting that maximum value out of it because there is a internal resistance present in the cell. Okay, so the internal resistance is basically present inside the cell. You cannot cut it and remove it. It is a part of the cell itself. So this is the thing that is trying to drive the charge. This is the thing that is trying to stop. Don't do it. Okay, so this is the internal resistance. Even though it's very low value, ideal cells have zero internal resistance. Okay, opposition offered by the electrolyte inside the cell. Obviously a electric cell have electrolytes present in it. Okay, maybe it is the form of liquid, maybe it's a dry cell. Okay, there are different types of electrolytes. So the electrolytes present in the cell, it tries to stop that current whichever being tried to do by this EMF, right? EMF is trying to push the electron out and the internal resistance is saying no, go it slow, do it slower. So internal resistance is basically trying to stop that flow and providing a resistance, right? That is the meaning of resistance. Resistance is basically which is trying to stop whatever is going to happen, right? So opposition offered by the electrolyte inside the cell causes a voltage drop I into small r. Small r is the internal resistance, okay, whenever current flows. Okay, so there is a formula given. We will discuss about these formulas once we come to that part, but for now just keep it like to a circuit basically. So when you have a cell, normal cell, okay, suppose you have now the symbol of the cell is this, right? Symbol of the cell is this. Now what is the difference between cell and a battery? Battery is basically when you connect multiple cells together, that is called a battery. This is a battery, this is a cell. Okay, now this is the ideal battery, this is an ideal cell. Now in practicality there is a small resistance involved with it. Okay, we are not talking about battery today, so let's erase that. So this is a cell. If you just measure it using some device across this cell, you will get a value which is EMF of the cell, generally denoted by epsilon. For simplicity we sometimes denote it by E, because epsilon is writing and remembering everything is confusing, so you can write capital E or you can use epsilon. Okay, so this is the EMF of the cell. Now when you connect it to a circuit, circuit means some resistance, obviously external resistance. When you connect it across an external resistance, some current flows through it, right? And this I into R actually gets deducted from the output. Okay, so the output that you are going to get, is epsilon minus I into R. This is the output that you are getting. So you are promised that, okay, I will give you epsilon amount of potential, but when you are connecting in a circuit, you are getting something less. Now you are complaining why it is less, because the internal resistance of the cell is eating up some of the potential, and output, the terminal voltage is slightly less. Now it obviously depends on the current. Okay, so terminal voltage is not a fixed value like EMF. EMF is a fixed value, by the way. EMF is fixed. EMF is fixed value. Okay, and this small r is also fixed, right? But if you see here, the current is not fixed. Current depends on the capital R. Current depends on capital R, like epsilon divided by R plus small r. So if you change capital R, if you increase the capital R, I value decreases, the potential drop is very small across the internal resistance. But if the R value is high, R value is small, then the current flowing in the circuit is very high, and the drop that you are getting across this will be very significant, and you will get a very low terminal voltage. The terminal voltage is not fixed. It depends on current I. It depends on current I. Okay, so that is one point. Okay, now let's move on. Cells in series. So when you are connecting some cells in series, basically I'm not doing the derivation. If you really want the derivation, I have done one short video of current electricity chapter where I have discussed all cells in parallel, cells in series in detail. You can go and check that out. The description I will try to give you in the comment section below if you really want about that derivation, right? Let me know in the comment section below, sir, I do want that derivation, please help me out. I will give you the exact time where the derivation was there in the one shot video, right? Now let's see cells in series. So here we have epsilon 1 R1, epsilon 2 R2, epsilon 3 R3. So three cells having three different EMFs and three different internal resistances. They are now connected in series. So when you connect them in series, what happens is the overall EMF of the circuit increases. How? It just adds up, epsilon 1 plus epsilon 2 plus epsilon 3 plus ... epsilon n. So when you are doing the epsilon, when you are adding up the epsilons, the overall value increases, right? Equivalent internal resistance is given by R1 plus R2 plus Rn ... So internal resistance also increases. So it has its pros and it has its cons. So what are the pros? Pros are that everything is increasing. The epsilon value, total epsilon value is increasing. What is the con? The internal resistance also increasing, right? So that is what series connection is used for. If you want to increase the overall EMF, output EMF, you require a high value, high voltage, then you use series combination. Most common circuits generally use series combination. For example, your remote system, your remote control car system, okay, all these devices. So if you have a blood pressure monitoring device in your home, that also uses series combination of cells. Okay, so even the backup system, UPS, okay, if you are using an UPS which provides backup to your computers, that also works on series combination of cells. Okay, maybe inverter battery also, if you have inverter battery, also works on the principle of series combination of cells. Okay, but here you are increasing the voltage, but also the internal resistance also gets increased. Okay, now what is the current through the circuit? Current through the circuit is epsilon equivalent divided by R plus R equivalent. Same formula, only the epsilon was replaced by epsilon equivalent and small r is replaced by small r equivalent, right? So this is the basic concept. So if you want to increase the EMF, the only way to increase the EMF is connecting them in series. Only way to increase the EMF is connecting them in series. Okay, and one more important point in series combination of cells, okay, the current remains same throughout the circuit. Okay, and another point that I always tell you, that for a cell, remember always whatever current exit the cell, same current has to enter the cell as well, right? I discussed it in another video also. So remember, this is a very basic concept about cells. Now let's move on. Series combination, KCET special. Now if you have, say, n number of cells connected in series and they are identical, if they are identical, then what you need to do? So identical means all of them have same internal resistances, all of them have same EMFs. So in that case, the current is given by N epsilon divided by R plus NR. Okay, so if N such cells all of them have epsilons connected in series, the equivalent EMF is given by N epsilon, epsilon plus epsilon plus epsilon plus epsilon plus. So N times it will be N epsilon. Based on this, we have seen questions, so please listen carefully. All the internal resistances are also R, so R plus R plus R plus R plus R, so R equivalent is NR. If n number of them are there, it will be N into R, right? Now what about the current in the circuit if you connect them in a series combination with a resistance R? If you connect them in a series resistance R, the equivalent current in the circuit will be I equals to N epsilon, the equivalent EMF divided by external resistance plus NR, right? This is the current in the circuit. This is the current in the circuit. So be careful, you need to be little careful to answer this question. Okay, so it will be N epsilon divided by R plus NR. We will see the parallel same condition, parallel combination also, don't worry. Now if R value is very small, R value is very small compared to this N R, that means the external resistance is small, say 1 ohm, okay, and the total internal resistance of the cell is 100 ohm. Okay, then you can ignore it and the approximate current can be calculated as epsilon divided by R. Okay, epsilon divided by R. Now if one cell is reversed, okay, it will be the equivalent EMF will be N minus 2 by into epsilon. If two cells are reversed, it will be N minus 4 epsilon. Okay, so let us understand that as well. So if you have 10 cells, suppose 10 cells are there. Out of the 10 cells, 8 of them are properly connected and 2 of them are wrongly connected. Wrongly connected means they are inversely connected. Okay, now you connect these two across a certain resistance. Okay, now if you connect it across a resistance capital R, what will be the current? So that was a question came in 2022, I think, or 2023. So epsilon, 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 epsilon. Okay, each of them have R. So if how many of them are properly connected? Properly connected. So it was mentioned that N number of cells. Out of N, 2 are wrongly connected. So N minus 2, these are properly connected, right? So this is the connection of the proper connection, but 2 of them are wrongly connected. That you cannot ignore. They are actually in reverse order. So you have to subtract another 2 epsilon from it because they are reducing the overall voltage. So that means it turns out to be N minus 4 epsilon. Okay, and the current becomes N minus 4 epsilon divided by R plus NR. Internal resistances are friends, they always adds up. They do not do things like this. Oh, you are properly connected, you are wrongly connected. No. Internal resistances, they always adds up. External resistances always adds up. But the EMFs has to depend on the polarity. Now if there are 2, it will be N minus 4. If there are 3, N minus 6. So twice. So if N number of cells are there, out of N number of cells, M cells are wrongly connected. The equivalent, this is total number of cells. Total cells are N, reverse connection is M. Then what is the EMF? EMF will be, remember this, N minus 2M epsilon. This is the equivalent EMF. Okay, this is the general formula. If you remember it, basically obviously you can do it like this as well, but if you do it, if you remember it, it will save you some 5-10 seconds, right? Let's move on. Next is cells in parallel. Again, when the cells are connected in parallel, if all of them are same EMF, the equivalent EMF becomes same as one cell. Okay, so if you are suppose epsilon, 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 when you are connecting them in parallel, the equivalent EMF becomes same as one of them. Okay, and if they are not same, then what is the formula? Suppose they each of them have epsilon 1 r1 like that, so you need to take individual EMFs divided by the by its own internal resistance, okay, then divide by their internal resistance in the same form, 1 by r1 plus 1 by r2 plus 1 by r3, okay, dot dot dot. So this formula is much easier to remember and without any difficulty. Okay, r1 into epsilon 1 or r2 into epsilon 1, or is there a plus or minus? So you don't need to worry too much about it. You just use this formula. That is the easiest way if the EMFs are not equal. If the EMFs are equal, remember the EMF remains same. Okay, so parallel combination of cells are used to give you a stable output voltage. Parallel combination of cells are used to give you a stable output voltage. Okay, equivalent internal resistance is given by R by M if M number of cells are connected in parallel. So suppose M number of cells are connected in parallel, equivalent resistance is R by M. Okay, current through the circuit is M epsilon divided by MR plus R. Now let's look into that as well. So if all of them are same, okay, equivalent EMF, we see that that is epsilon. Okay, R equivalent is given by R by M. Suppose M identical cells are connected in parallel. Okay, then what happens? E equivalent is epsilon, R equivalent is R by M. Now we have an external resistance capital R as well. So current will be E equivalent divided by external resistance plus equivalent resistance of the cell, right? Let's put those values. It will be epsilon divided by R plus R by M. Okay, so that will be epsilon by R into M plus R whole by M. So it will be M epsilon divided by R plus MR. Right? Interesting. So this is not the same as the previous one. For series, this M was here. For parallel, this M shifted to capital R. Right? So there is a slight change over here as well. Okay, now if unequal cells, this is the unequal cells. I think I already discussed this. If the only two of them are there, R1 R2 by R1 plus R2, same as parallel combination. Okay, some points are noted over here. Now again, remember that you can use the shortcut formula that I told you. Okay, mixed grouping you need to solve it based on how many of them are series, how many of them are parallel. But one very important point is that the power maximum, when the cell will spend the maximum amount of power, which is very important point to remember. The maximum power spent by the cell is when the internal resistance is exactly equals to the external resistance. If internal resistance becomes exactly equals to the external resistance, the power becomes maximum. Okay, and for maximum current condition is R must be NR by M. Okay, maximum current is given by NR by M, and the maximum current can be calculated N epsilon by 2R. And if the maximum power, that if you want, maximum power is basically so this is a shortcut of all the formulas that we have learned. For your reference, you can remember it. Not everything is for example, last two is not that important, but first three are super duper important, so try to remember them if possible. Now let's move on with some questions. 4 identical cells, each of EMF 1.5 volt and internal resistance 0.5 ohm, are connected in series across external resistance 4 ohm. The current in the circuit is. So 4 identical cells, each of EMF 1.5 volt. So 4 cells You don't need to draw that in the exam, by the way, if you are understood the problem. Okay, if you have understood the problem, you don't need to draw it. Okay, now 4 cells, each of EMF 1.5 volt and internal resistance 0.5. So what is the equivalent EMF? 4 into 1.5, that is 6. And what is the R equivalent? R equivalent is 4 into 0.5, that is 2. So what is the current in the circuit? The external resistance is 4 ohm. So the current in the circuit is given by 6 by 4 plus 2, that is 1 ampere. Okay, that is 1 ampere. So correct answer is option B, 1 ampere. Okay. Now let's move on to the next question. 4 identical cells, epsilon 2 volt R 1 ohm, are connected in parallel across an external resistance of 2.25 ohm. The current in the external resistance is. So here we have 4 cells, each of EMF 2 volt and internal resistance 1 ohm. Internal resistance 1 ohm. Okay, so what is the equivalent EMF here? All of them have same voltage, so equivalent EMF will be also same. In parallel combination, voltage remains same. So because all of them are equal, so the equivalent EMF will be 2 volt. What is the R equivalent? R equivalent will be 1 by 4, that is 0.25. Okay, so what is the current? Current will be epsilon equivalent by R plus R equivalent. Now this is given by 2.25, so it will be 2 divided by 2.25 plus 0.25, which is 2 by 2.5, which will be slightly less than 1 ampere. Let's see, 8 by 10, that is 0.8 ampere. It will be 0.8 ampere. So if you see the answer, 0.8 ampere is the correct answer. Let's move on. Capital N cells arranged in parallel rows with the cells in series per row, driving current through external resistance capital R, current maximum when R is equal to NR by M. Okay, so this is a mixed grouping. If N cells are arranged in M parallel rows, N cells in series per row, then the current is maximum when resistance is remember parallel, series by parallel. So this is series and this is parallel to series in by parallel into internal resistance. Okay, so remember R is equal to number of cells in series by number of cells in parallel into internal resistance. If equal cells are connected in series and parallel, this is the condition for maximum current. Question number 4. 2 cells of EMF 4 volt and 2 volt with internal resistances 1 ohm each are connected in series so that they oppose each other across 4 ohm the current is. So first of all, they are connected in series. So connected in series means, suppose one of them is 4 volt, another one is 2 volt. They are opposing each other means they are connected in reverse order. So this is 4 volt, this is 2 volt. Each of them have internal resistance 1 and they are connected across an external resistance R. Okay, so oppose means they are very careful. Oppose means they are in reverse order. The external resistance is 4. So what is the equivalent EMF? Equivalent EMF is 4 minus 2, that is 2. What is the equivalent internal resistance? Equivalent internal resistance is 1 plus 1, that is 2. So what is the current? Current is equivalent EMF divided by R plus R equivalent, that is 2 divided by 4 plus 2, that is 2 by 6, that is 1 by 3. Okay, so it will be 1/3 ampere. So 1/3 ampere is the answer as well. Now last problem of the day. 2 cells, epsilon 1 equals to 6 volt, R1 1 ohm, epsilon 2 3 volt, R2 2 ohm are connected in parallel like terminals together. The equivalent EMF of this combination is, so 6 and 1, 3 and 2, so 6 by 1 plus 3 by 2 divided by 1 by 1 plus 1 by 2. That's it. Equivalent EMF. This is the formula. Okay, 6 by 1, 3 by 2, 1 by 1, 1 by 2. Okay, so it will be just do the LCM. 12 plus 3 by 2 divided by 2 plus 1 by 2, 2 cancels, and you get 15 by 3, that is 5 volt. The equivalent EMF is 5 volt. So correct answer is 5 volt. Right, so this is the end of today's session. If you have any questions, any doubts, please feel free to ask me in the chat. Okay, so there is a summary for all of you. Series EMFs added, resistance add best when R is large, parallel EMF unchanged, identical cells, R divides by M best when external resistance is small value. Okay, mixed grouping gives maximum current when MR is equal to NR. Okay, reversed cell E equivalent is equal to so you have to minus the number I have already discussed. Unequal parallel cells, epsilon 1 R1 is equal to epsilon 2 R2. Okay, so this is the easier formula to remember. Right, I hope that you enjoyed today's session. If you still have any questions, any doubts, please feel free to ask me in the comment section. I'll be back with a chapter, another short topic very soon. Till then, bye.